Hello everyone. This video is about a faster way to compute matrix multiplication known as the row column rule. In addition to that, we'll see some properties of matrix multiplication. Let's have a look at how the row column rule works. Suppose you have two matrices like so, A of size m by n. I've written down the general format for the matrix A, and B of size n by p. Remember that these matrices can be multiplied to one another because the number of columns of the first matrix matches the number of rows in the second matrix. Here's how we can multiply matrices in a more efficient way without using the definition. Our goal would be to give a formula for every entry in the product matrix. AB will be a matrix C. The entry Cij is obtained by multiplying as vectors the row, the ith row of A and the jth column of B. So how will this work? This is the ith row. And this is the jth column. Notice that for this setup, we may think of the ith row of J as a matrix, and we know how to multiply a matrix times a vector. So the way these two will be paired up will be that AI1 will be multiplied with B1J, and then so on. If I have A12, this will be matched with B2J, and so on, all the way up to AIN times BNJ. So the way I will compute this multiplication is here. I'll do AI1 times B1J, and that's going to be my first summand. And then I'll put A12 times B2J, that's going to be my second summand. And then all the way up, I'll do A13 B3J, all the way to AIN BNJ, which is my last summand. This all added together will give me a number. That number is the ijth entry of my matrix. Let's have a look at it in an example. These are the same two matrices that we used in the last video, but this time we will compute this product using the row column multiplication. The first entry here is entry 1, 1. It will involve the first row of B and the first column of A. So the way I can compute this entry is by computing 1 times 1 plus 2 times 1 plus 3 times 1. When I do that, I get 1 plus 1 plus 2 plus 3, that's a 6. Let's have a look at this entry here. This is row 2, column 1, meaning that I'll have to use the second row of matrix P and still the first column of A. When I do that, I get 4 plus 1 times 1, it's 4, plus 3 times 1, it's 3. 1 times 1 is 1. So it's 4 plus 3 plus 1. That's an 8. Let's compute the other entries. For first row, second column, I will have to look at the first row of B and the second column of A. So I'll have 1 times 1, that's 1, plus 2 times 0, that's 0, so it's still 1, plus 3 times 1, so it's 1 plus 3, that's a 4. Let's do, for the second row, I'll have 4 times 1 plus 3 times 0 plus 1 times 1. That's 4 plus 1, which is a 5. Let's do the third row. This time I will multiply the rows of B with the third column of A. So the first row times the third column will give me 1 plus 2 plus 0. That's a 3. And the second will give me 4 plus 3 plus 0. So it's a 7. Last column, when I multiply these two rows of B by the last column, the only entry that survives is the first one. So I get a 1 and a 4. You don't reduce the number of computations, but you can write a little less. And it's a little bit more intuitive to compute matrices this way. Let's have a look at another example. A times B. Well, let's compute A times B in this case. First of all, let's think about the size that we should get. This is a 2 by 3 and this is a 3 by 3 matrix. So I expect A times B to be a 2 by 3. First entry in the first row and column of A times B is the first row of A times the first column of B. First column of B only has a 1 in the second entry. So it's 1 times 0 plus 2 times 1 plus 3 times 0. When I look at the second row, by the same token, I get a 3. Then I switch to the second column, which means take the rows of A and multiply them with the second column of B. First row times second column gives me 1. Second row times second column gives me a 4. Let's have a look at the third row. 1, 2, 3 times 0, 0, 1 just gives me a 3. And 4, 3, 1 times 0, 0, 1 gives me a 1. Here's your multiplied matrix. Now let's have a look at some other properties of matrix multiplication. I will mention these briefly and will mostly focus on just one of them, which is maybe the most surprising. Whenever we multiply matrices and there's a scalar involved, the scalar commutes with matrix multiplication. So we can unload it to the first matrix or to the second. Matrix multiplication is associative. If I'm multiplying 3 matrices, I can multiply first the first 2 or the last 2. Matrix multiplication is distributive. A plus B times C is A times C plus B times C. Distributive both on the left and on the right. These are different properties because matrix multiplication does not commute, as we said in the last video. So they need to be stated as different properties. Multiplying any matrix by an identity matrix gives back the matrix itself, and multiplying it by a 0 matrix gives back a 0 matrix. Now let's have a look at this last one. The transpose of a product is the product of the transposes, but look at the order in which the product happens. We have A times C transpose is C transpose A transpose. Let's try and make sense of why that is happening. There's an order reversing relation in here when we look at transposes. Well, let's think about it this way. Let's use the row column rule. If I were to compute A times C, I've sketched them here. So A has K rows and M columns, C has M rows and N columns. The ijth entry of A times C is obtained by multiplying the ith row of A with the jth column of B. So I'll look at these entries here and I'll add them up one by one. If you think about them for a second, well, the first summand you get is AI1 times C1j. Those are the first entries here and here, and so on and so forth. You have AI2 times C2j all the way to AIM times CM. That is the entry in the ij place of the matrix AC. Now let's look at the transpose. I sketched the transpose matrices here. So C transpose will have n rows and m columns. A transpose will have m rows and k columns. So now let's track what happens to the ith row of A. It has become the ith column of A transpose. Similarly, the jth column of C has become the jth row of C transpose. In other words, when I compute C transpose times A transpose, this is C transpose and this is A transpose. When I look at the jth entry in C transpose A transpose, I will be multiplying the same entries as before. I will have my CJ1 here and my A1I here. So on, the second one will be CJ2, and this will be A2I. If you look at the summons that you get by just switching their order, A1I, CJ1, you will realize that these summons are exactly the same appearing here. Did I write them right? It's a transpose matrix. So this is C1J, and this is C2J. Was a little mislabeling there. Yes. Well, if you stare at these long enough, give me a second. Okay, let's try this again. The entries here are exactly as they're written now. This entry, for example, is AI1, and this is C1J. First row, jth column, ith row, first column. When we transpose them, this is what we get. The entries AI1 that was here just becomes the entry that is up here. And C1J just moves to the jth row of C transpose. So when you multiply them together, you get this product here, which if you switch the factors becomes AI1 C1J. It's a 1. And then all the way up, every one of these factors, if you switch the order, AIM, CMJ. In other words, the JI entry of C transpose A transpose is the same as the IJ entry of A times C, which is what we wrote up here. But the IJ entry of A times C is the same as the JI entry of AC transposed. This was a tongue twister, but the conclusion is, so the reason why these get swapped is that rows becomes columns when I transpose. The conclusion is that the JI entry of C transpose A transpose is the same as the JI entry of AC transpose. But then it means that the two matrices must have the same entries. And so it's only natural that AC, when I transpose it, I get the transpose of C times the transpose of A with the reversed order. let's move on to the next definition. This is a very important definition. We say that a matrix is diagonal if it is a square matrix that has zeros everywhere except possibly on the main diagonal. So let me just draw maybe a 3 by 3 diagonal matrix. It can only have non-zero entries in the what is called the main diagonal. In other words, its only non-zero entries are entries AII, where the index of row and column is the same. Another example could be a 2 by 2 matrix like this. Now, let's think about these two questions. If I have two matrices, A and B, and suppose that they're diagonal over the same size, then A plus B will be diagonal as well. Suppose that my matrices look like this. So there's going to be, well, I'll write it as follows: A11, and then zeros all the way down there, and zeros here. That will be A22, and then zeros all the way down to A and N. And B, let's suppose it is the same. B11, and then zeros all the way down here. Here are their zeros, and then just B and N on the diagonal. Clearly, when I sum them, since summing them is keeping entries in the same place, I will get A11 plus B11, and then zeros all the way elsewhere, A22 plus B22, and then zeros. These are all zeros, A N N plus B N N. In other words, it is true that A plus B is diagonal. Now, A times B is also diagonal. And let me move to the next slide where we can compute it a little bit more cleanly. We will actually prove two things together. I will show to you that A times B is diagonal, and moreover, for diagonal matrices, AB is indeed equal to BA. So diagonal matrices can be switched when you multiply them with one another. Let's try and see why that is the case. When I multiply these matrices together, I get, well, for example, if I look at the first entry here, I'm multiplying the first row and the first column. So when I do that, I get that A1 times B1 will be in the first entry, and then nothing else, because everything else is zeros. But now, if I look at, for example, this second entry here in the second column, I will be multiplying the first row of A with the second column of B. And the second column of B has 0, B2, and then other zeros. So I will have A1 times 0 plus 0 times B2, and then all the rest is 0. So I get zeros here, because the non-zero entries in the first row and second column don't match. It will be the same for all of the other multiplication that I have to do. The only way that they can match again is, for example, let's look at the second column of B. This will match with the second row of A, because in that case, I will have 0 times 0 plus A2 times B2, and that will become my entry here. And then all the others will still be zeros all the way. In other words, everything in this product will be a 0, except for entries that were on the diagonal. So if we look at this product matrix here, we'll see that since AI, BI, these are numbers, so this is the same as BI, AI, which are the entries for B times A, this implies that A times B is a diagonal matrix with entries the same as the entries of B times A. We haven't computed B times A, but the reasoning is exactly the same, and I encourage you to try it and check that you actually get these entries out of that. Okay, this concludes the video about properties of matrices and the row column rule.